Well, there you go. All right, so is this one we ended on? Okay, very good. So you're going to have to follow the bouncing ball a little bit because we're going to not finish this part before we go on to another part. You'll be fine. But we've talked about chemical reactions can be exothermic or endothermic, right? We talked a lot about that. And the whole recap thing says you can know how much heat was evolved or how much heat was required by the delta H of the Rxn, the enthalpy of the reaction, okay? Endothermic reactions are what? Positive. Exothermic reactions are negative, okay, for the delta H. All right, so one more thing I want to talk about right now is the fact that if you know how much energy a chemical reaction has given off or required, you can do this sort of stoichiometric calculation if you have the balanced equation. So here's how it looks. For example, when iron combines with chlorine, it's exothermic. Negative 799 kilojoules of energy is evolved. Okay, but remember that's per what? 2 moles of iron, that's per 3 moles of Cl2, that's per 2 moles of FeCl3. It's specific for that particular stoichiometry, that particular set of stoichiometric coefficients. Okay? So we're going to work a problem, and I'll go ahead and write it underneath here. How much energy, so I'll put question mark energy over there. How much energy is released when you have 2.35 grams of iron? That's the question. Okay. So I'm going to show you, I have another slide to kind of bring this out, but do you see what we're going to use to our advantage is that we know that 799 kilojoules of energy are released for every, check this out, 2 moles of Fe. How do we know that? Because that's what it says. Okay? So we're going to use that to our advantage. I lost my blue one, so now I'm on to magenta. So with regard to stoichiometry and energy, so for instance, we could say a few things about this equation that we're working with in that enthalpy of reaction. We could say 799 kilojoules of energy are released for every 2 moles of iron. Actually, that's the one we're going to use. We could focus on the Cl2. We could pick off the stoichiometric coefficient in front of the Cl2. Okay, we could say 799 kilojoules of energy are released for 3 moles of Cl2. Alternatively, we could turn our attention to the product. We could say 799 kilojoules of energy are released for the stoichiometric coefficient in front of the FeCl3 is for every 2 moles of FeCl3. They're just depending upon what we need. Yeah?
Does the sign not matter in those ratios?
I think the reason this slide says as it does is it's implied there, released. I'm kind of like you. I would tend to want to go like this.
Yeah.
I would tend to want to do that. But it's a little bit redundant, a little bit, not too much redundant, if you say released negative 799 kilojoules of energy. So that's why that is. It's a subtle thing.
And that one's positive because it's the product, right?
Oh, no, that's not.
Okay.
You're right. Thank you.
It's like, wait a minute. Okay, so that one's still negative.
Yes. Thank you. Good catch. Yes, energy is released in all those cases. I think I got like into Hess's law in a minute, so. Okay.
We're not there yet.
No, we aren't. Okay. So back to the whole, 2.35 grams of Fe. So let's work that problem. So we're going to start with 2.35 grams of Fe over 1. And we're going to convert that to moles using the periodic table. The molar mass of iron is 55.85 grams per mole. So that's from the periodic table. Now our grams will cancel. We're left with moles of iron, moles of Fe. And now we can just go ahead and insert that first ratio. And I'm like, I'm kind of like what you guys have been saying or what Marie's been saying. I think I would go ahead and put a negative there. I like that much better. because then my answer is going to be negative. I'm like, dang, that is exothermic, isn't it? Okay. So notice that grams of Fe cancel. Okay, and now moles have canceled, and we're left with units of kilojoules. We're done. We're totally done. Rounded to 3 significant figures, the answer is 16.8 kilojoules of energy is released. So actually, remember in how I did it, I put a negative here, and I would put a negative here. I really would. And I think it's probably down here. Oops, no, it's not. So did you catch my correction on my slide? I really would put a negative.
So for our homework, if we didn't put the negative sign, would we really need to state it?
Yeah, that's the problem, is it comes back to bite you in the butt. If you don't use the words "was released" and you didn't put a negative sign, then you're like, AOL. But if you just simply put negative 16.8 kilojoules of energy is associated with the reaction of 2.35 grams of iron, then you're covered.
And then if it absorbs energy, we just don't need to put it.
That's true.
Yeah,
If it absorbs energy, it is positive. The sign of the delta H, or the energy. Yep. Okay. So now we have some problems. I have some hints to those problems. And I'll take a screenshot of this and kind of throw it up under Twitter if you tend to do that. The reason these hints are up there, let's see, if you want to write down the hints, because I see you guys don't have hints. For problem 15, you want to note that 1 mole is equal to 22.414 liters. We'll be talking about gases in Unit 5 in here, and then that will make more sense. But that should get you down the road. Also, for the next part, for the same problem, 715, but part C, okay, you just need to, when they deal with the species C4H10, you need to know that the moles is 0.503. Again, something we haven't necessarily talked about. I think that's a gas also. And then, for the last problem, 17, for part B, you need to know that when it talks about methane, CH4, the amount of methane in that problem is 696 moles. Okay? Since it's not in my lecture notes, so you know that since those have been went to press, that I've since made these notes to students, because students be like, I can't do that one. I'm like, oh yeah, you can't. So with those, you should be able to. So let's take a quick look at them. There. Okay, so for this one, I've kind of diagrammed it for you. It's very similar to the one we just worked. Notice it's exothermic, and it says that the product, okay, the calcium hydroxide, CaOH quantity 2, that you're looking at how much energy is released in kilojoules if you produce 238 kilojoules of that. Okay, so I can't remember what hints I did. Okay. So again, some of these hints I'm sure don't need. But I would go from kilograms to grams of the calcium hydroxide, use the molar mass of calcium hydroxide to moles, and then just kind of plug in that ratio right there. The next one, there's your chemical reaction. It's also exothermic. And again, you're supposed to come up with how much heat is evolved if you have 1 gallon of C8H18. Notice since it's given in volumes, you're going to have to do some manipulation to get it to moles, basically. So that's kind of the front end thing of that. So here's my little hint. I would go through liters. I'd go gallons to liters, and the density is given in milliliters, so I'd go from liters to milliliters. Plug in the density to get to grams, and then to get it to moles, you're going to use the molar mass of the compound. And then once you have it in moles, you can go ahead and finish her off. Then 15, I had for B and C some notes. Okay? So for A, you don't need any notes. Okay? So basically for A, it gives you the mass of C4H10. And again, how much heat is evolved? Okay, it's exothermic. That's A. Not too bad. Now B gives you the volume of a gas, and B refers to STP, stands for standard temperature and pressure for gases, which is different than standard temperature and pressure for thermodynamic problems. But anyway, my hint, I gave you how many moles I said use 1 liter is equal to, 1 mole is equal to 22.414 liters. 1 mole is equal to 22.4 liters. You have liters, so put 1 mole over 22.414 liters. Your liters will cancel, and you'll be left with moles. You're ready to rock and roll with that one. Okay? So you'll go to moles from liters using that equality statement, and then once you have moles, then you go ahead and do it like we've been doing it. The next one, again a gas, and unfortunately this one isn't at standard temperature and pressure. We'll talk about how do you get moles if I'm given the temperature and pressure, okay, and volume, I guess. Temperature, pressure, and volume, how do I get to moles? We'll talk more about that later. Some of you guys know, use PV equals nRT and solve for N. But anyway, I'm solving for N for you. The moles that you have to work with of the what is it? The C4H10 is 0.503 moles. So I made that one a little easier for you. And the last one looks like this. It's also got 3 parts. The first part, it changes it up a little bit. It says, hey, I know that this amount of energy is released, 2.8 times 10 to the 7th kilojoules. That's a lot of energy, right? And it wants to know how much CH4 did you burn, so in grams. So in this case, your first term is going to be your energy, okay, over 1, okay, and then you're going to use that kind of stoichiometry. So you're going to put moles over energy, okay, get to moles, and you're going to use the molar mass to get from moles to grams. Similarly, or kind of similarly, B actually gives you, again, a volume, pressure, and temperature, and I'm telling you what the moles are. So I told you that the moles is whatever I said on that thing, because I don't have it here. Oh, yeah, here it is. I told you in my hints that the moles to use is 696. So again, you're going to start with energy, and you're going to backtrack to, no, if they give you moles. You're going to start with moles, and then you're going to go to energy. And the last one, if you read C down here, it says, if the quantity of heat calculated in part B could be transferred with 100% efficiency to water, what volume of water in liters could be heated from 8.8 to 60.0 degrees Celsius? This is a Q is equal to MC sub P delta T problem. Okay, so here's my hint for that one. Basically, you're going to take your answer from B, which is energy released, and you're going to think of it going ahead and heating this water here that I'm drawing. What do you know about the water? Well, you don't know the mass. You know the specific heat of water. You know the initial temperature and the final temperature of the water. So basically, in the Q is equal to MC sub P delta T for this, your Q is going to be from your B. Okay, so that's that one. It's all good. Okay, so this is what we're going to do. We are going to skip the rest of part 4 for now. Just trust me on this. And we're going to go to part 5. And then we're going to go to part 6. And then we're going to come back and pick up the rest of part 4. So if you're one of those personalities that hates skipping around, this is just a test to you. Okay, so on to part 5. It should look like this. Hess's law. So many S's in Hess's law. So basically, you have, in Hess's law, problems, or Hess's law, you have some sort of chemical reaction, and I usually call that the chemical reaction of interest. Usually, it's maybe a complicated chemical reaction, okay? But it's a chemical reaction that you do not know the delta H of. Delta H is equal to question mark. You don't know the change in enthalpy for that reaction of interest. And to work this sort of problem, though, what you do know is, sometimes call them baby steps. Okay, basically you know, like I'll call this equation 1, oops. Call this equation 1. You know, you have a little equation 1, delta H1. A little equation 2, delta H2. Little equation 3, that's my equation. And you know the enthalpies of reactions for those. And the cool thing about it is, and I'm going to show you, how do you add up equations? Those are equations. How do you add them up? Well, you basically center along the reaction arrow, add all the reactants, add all the products, kind of bring them down. That's it. So when you add these all together, you get, it's like magic, you get the overall reaction of interest, RxN of interest. And like this already says, if you can come up with the reaction of interest by adding these smaller equations with known enthalpy values, then all you got to do is add these together to get delta H of the overall reaction. That's it. That's Hess's law. So I'm going to do one example for you. But that's kind of the overall thing. So the only reason Hess's law works is because enthalpy, changes in enthalpy, are independent of path. And the opposite of dependent path, independent path. Independent path is a state function. I only care where it starts and where it ends. This whole idea of having 3 chemical reactions, for example, kind of diagramming how you get from how you actually accomplish a reaction, it doesn't have to proceed by those 3 chemical equations, as long as they mathematically add up to equal the overall reaction of interest. Okay? So, here we go. So we are going to do an example, the combustion of benzene. Benzene is C6H6. This is balanced, which we are going to need to use a balanced equation to do Hess's law. Okay. And that's the reaction of interest. That's the overall reaction of interest. And here are the baby equations. Okay. So overall reaction of interest. In fact, sometimes that's how I do my answer keys. This is RxN of interest. Okay. And these are, I don't know if I even label these. Gosh, I've done that a lot. That is like a heavier pen than usual, I think. Okay. So one of the things I really like, I would really suggest you do, is I would number these things. I call them my puzzle pieces, kind of. I would just slap a number on those so fast. Those are like your puzzle pieces. Because, do you see where actually we can refer to the enthalpy changes? I mean, we can use that little subscript, which indicates which puzzle piece it is. We can use subscripts on the enthalpies of. That just kind of helps stay organized. All right. So I will never give you a Hess's law problem where you don't have to use these puzzle pieces to manipulate them somehow to get the reaction of interest. I don't do that. Okay. Some are easier than others. So let's see how we would do this. Before we do that, the reason I want to talk about allotropes, by the way, is only right here. You see where it says carbon? Okay. Carbon, well, we know what carbon is, and it's in its solid state. But specifically in its solid state, it was a particular allotropic form called graphite. So I just want to kind of walk you through. I'm picking on carbon, and I want to tell you that carbon isn't always graphite. Solid carbon is not always graphite. There's this idea of allotropes. It sounds like isotopes, doesn't it? Allotropes. So allotropes are the same element in the same physical phase, I believe, but just slightly different form. So actually there are 3 allotropic forms of carbon. You know them, right? Because like a diamond, what is a diamond? It's carbon, right? What if you have a lead pencil? Isn't that funny how lead pencil actually is just like graphite, carbon graphite? That's a second allotropic form of carbon. So allotropes are they just amaze me. So we'll kind of take a look at diamond versus the graphite in your pencil. Kind of from left to right, you see the graphite in your pencil. The middle one is a diamond. And the black one over there, or the last one, the C actual, is how carbon atoms can arrange themselves in something called buckyball. Is that not cool or what? And I'm thinking this is right. I'm thinking that they found this form of carbon actually from outer space. I think this is actually associated with, like, must be like low pressure environments in meteorites. So the black balls are all carbon. This is carbon as it exists in a diamond. This is carbon as it exists as graphite. Kind of has that layered sort of thing going. And this is carbon as it exists in forming a buckyball. Yeah, I have buckyballs in space. So, okay, so that's the idea of an allotrope. Now back to the problem, okay? So the thing with the red box around it, that is our goal. That's our reaction of interest. So put another way, I'm going to put question mark delta H, Rxn. We don't know the enthalpy of that reaction. That's what we're trying to get to. So here's how we go. We'll take them, I have slides. Basically, we're going to take them one at a time. And we're going to compare them with the reaction of interest. So let's look at the first one. So what you need to do is you need to look at your reaction of interest and find something in there that is also in your puzzle piece. So for instance, we are going to focus on the C6H6. Notice in my particular equation 1 that the C6H6 is on the product side. But on Wednesday, we talked about how we know we can switch number 1 around, swing it around the reaction arrow, and then all we got to do, what, is change the sign. Do you remember we talked about that? So actually, I'm going to go ahead and do this. And if I was working this problem like on just one sheet of paper, I would, down at the bottom, I would write, and I'm going to tell you the other convention I really like. Notice that this is one, we call this prime. 1 prime. The prime just simply means that it's related to the first one. Okay, but something's different about it. So what we did was we swung it around the reaction arrow. Now instead of having six carbons plus 3 H2s plus 1 C6 goes to form, 1 C6H6, we start with 1 C6H6 goes to form 6 carbons plus 3 H2s. That's it. So I would usually put that down, okay, and actually down here on my answer key, if I'm working this is kind of, I'm setting up my primes to go ahead and add them together, okay, because I can't really show you in the PowerPoint, but that's what I would do, okay. So that's my prime, but now I need an enthalpy change for 1 prime. Enthalpy change for 1 prime is the same value but opposite in sign. So instead of being what, endothermic, it's exothermic. And it does seem, there are some things we do where we just kind of, we have tunnel vision, we just kind of keep marching through the problem, and this is one of those. So then you set 1 and 1 prime aside and you look at 2. So here we go. Here is 2. Because you might be like, well, that doesn't fix this or that. Well, don't look at this or that. Just focus on one thing, see if you can fix it, and move on. Okay, so for this one, notice we have carbon dioxide in common, but I need 6 carbon dioxides, and I only have 1. This is my 2. So I can scale that thing up, can't I? And that's exactly what I'm going to do. For my 2 prime, I'm going to basically multiply by 6. That's it. And usually on my answer keys, kind of out to the side of 2 prime, I will say 2 prime is 2 times 6. I just kind of make a little note of myself, for myself. So 2 prime, we scaled everything up And so we could get our 6 CO2s, which matches now with the overall reaction of interest. And again, don't worry about anything else. It's like a Hail Mary at the end. Okay, so this would actually go under my 1 prime. So now I better scale up my delta H, right? So my delta H2 prime is going to be 6 times that negative 393.5. So my delta H2 prime is negative 2,361.0 kilojoules. And like I said, kind of that would be on the bottom of my paper, that means my second line. I kind of arrange my primes. Now it's possible sometimes we don't have to change it at all. We just need to, and then in that case I still call it a prime and I bring it down. I say no change needed. Okay, one more puzzle piece. So this was the third of 3 baby steps we were given, pieces that we could get the overall reaction of interest. So in this case, now and I haven't mentioned this, but notice how I'm ignoring the O2. Here's the deal. I'm ignoring the O2 here, quite frankly, because if you look back at one of your other equations, it also has O2 in it. So I guess I should be saying the thing that's unique to the thing that's unique to 3 in overall reaction of interest would be the waters. And again, it's kind of like the situation we ran into with the carbon dioxides. It's on the right side, so I don't need to reverse it. But I need 3 moles of it, so I better scale up my equation 3. So my 3 prime is actually going to be 3 times 3. So I would usually say 3 times equation 3. So if you take 3 times negative 241.8 kilojoules, you get negative 725.4 kilojoules. But don't forget, like for instance, you're like, really? Oh my goodness. So notice if we take 3 times 1/2, we get 3/2. We have to scale up everything. Don't forget to kind of scale up as you go. Scale up everything. So now at the bottom of my page, I have a 1 prime, 2 prime, and 3 prime. Okay? And it should look something kind of like this at the bottom of my page. One of the things I don't like about this PowerPoint slide is it doesn't line up my reaction arrows. Okay? I would usually line those up. I would have like reactants, and I would make it so products, they would all kind of line up. So now what we're going to do is we're going to add reactants, and we're going to add products. And the cool thing is, though, is if you see anything on the reactant and the product side anywhere, they can go ahead and cancel each other. They go away. I'll show you how this works. So for instance, do you see where, and again, I wish the reaction arrows all lined up. But can you see carbon? I have 6 carbons produced in my 1 prime, and I have 6 carbons consumed in my 2 prime. Those both go away. We could bring them down to and then cancel them at the end. We could do that too. Okay, let's see. See anything else up there that'll cancel? The 3H2s, yep. Those will cancel too. Very good. And I think that's about all that's going to cancel. So again, I kind of have a brick wall here. Here's my brick wall. We have reactants and products. All right, so the other thing as we write this, we need to combine terms. So you see I have 6 O2s and I have 3/2 O2s. And if you're like me, I need a cup of coffee to figure that one out. But I eventually do. Okay? So what? 6 is the same as 12/2. So basically you have 12/2 plus 3/2, so you have 15/2. Right? That's exactly what we do. this is the Hail Mary moment. This is the does it or does it not? Okay, so what we bring down is things that didn't cancel and we combine terms. So things that didn't cancel were this and these, and we combine those to that. And notice what didn't cancel on the product side were 6 CO2s and 3 H2Os. We bring those down. Okay. Sometimes for whatever reason, I'll just say students, because I don't think I've ever done this, but they tend to do a Hess's Law problem like this, and they don't do this part. This part is important. Because only if this is the reaction of interest can we now turn our attentions to basically adding together the delta H1 prime, delta H2 prime, delta H3 prime, and we're done. We are almost done. Okay, so that's like a check. You have to check it. Since our 1 prime plus our 2 prime plus our 3 prime is equal to our reaction of interest, we can go ahead and add, like I said, those enthalpies together and come up with the answer. So here we go. It shouldn't have been so dramatic. The delta H1 prime we had a few slides ago, negative 49.0. Delta H2 prime, negative 2,361.0 kilojoules. Delta H3 prime, negative 725.4 kilojoules. So we are adding them, so we're definitely going to get a nice big old negative number. Now remember, since we're adding, we're conservative with regard to decimals. So actually we're going to end up with 5 sig figs. But so if you add all those together, you get 3,135.4 kilojoules. Would be the energy associated with the energy that's released, right, during the combustion of benzene for that particular balanced equation, those sets of stoichiometric coefficients. That's a lot of joules. And I will just be careful of your rounding and such, so. All right. Are you serious? So let's take a look at these. These actually, I told you kind of I'm wrapping around to a year ago, like from what I did for those students. And it's like, I really gave them all that information. So let's take a look at these. These will also be due on Monday. What was I thinking? 768. But they're kind of fun. You either love them or you hate them. Oh, I wonder if I didn't. Yeah, shouldn't label yet. Is that the first one, 72?
68, no.
Oh. Oh, this still must be called. This one. Is that better? Okay, cool. So this is what 68 looks like. The star is the reaction of interest. Note that I really suggest you go ahead and label 1 and 2. Those are your things you get to work with. They kind of scream what they are because you know the enthalpies for those. Okay. So my hint was, notice that I put under purple, I'm focusing on the carbon monoxide. And so basically you have to reverse that puppy. And I went ahead and told you that the delta H1 prime is going to be positive instead of negative. Oops, really? Come back here. I hit the wrong button. Where did it go? Hints. 72. Okay. Oh, maybe it's under. Duh. All right. Don't hit the wrong button this time. Okay. So for the second one, if you focus on the carbon dioxide, I'm just reading my notes here, looks like it's on the correct side. And notice you only need one. So this is actually, you leave it alone. But I would suggest you do that, and then I just add them together. Notice if you add the purple plus the blue, by golly, you should get the one with the star at the top there. And if you do, you can go ahead and add delta H 1' and 2' to get the delta H for the reaction of interest. The next one, kind of similar. Reaction of interest, we have 3 puzzle pieces. And this one I don't belabor it nearly as much. So my hint for using the first baby reaction is to focus on the hydrogen. Looks like we need 2, and we only have 1. That's on the correct side. For the second puzzle piece, focus on the C3H4. It's looking pretty good. No manipulation required. I would still call it 2' though. 3', focus on the C3H8, which it's just on the wrong side. So we're going to reverse it and change the sign of the delta H. They're fun. Okay, you got the idea. Okay, the next one looks like this. Reaction of interest, 2 puzzle pieces. Focus on the Cl2. And for the second one, they kind of make your eyes go buggy after a while. You're going to focus on the C2H4, and you're going to actually find that you only need 1, so you're fine. Add, yeah, we got it. Okay. The next one, reaction of interest. We have 3 puzzle pieces. There's our hints for what you do with each. Oh, okay. So this one is finally something a little bit different. Notice that my note for puzzle piece equation 2 is to focus on getting a total of 4 waters. The problem with water here, if I remember this problem, is notice that water, and I'll go ahead and draw on this. Water, you of course need 4. That's cool. That's reaction of interest. But notice that it's a little complicated because you have you have waters in 2 of your baby equations. So this is where it becomes a little bit more interesting. Okay, so my hint for number 2 is you've already manipulated or created water in your first. So when you go to your second baby step or whatever, focus on the water. Just trust me. It will be interesting. Let's see, what did I say? Notes for last one. Focus on the H2O2. That one's a little more straightforward. The thing that's unique about water here is, like I said, it exists in more than one of your equations. So as you change one, you change, you know what I'm saying? So, okay. I think we have one more. No, that was it. Was that it?
Just 72.
Okay, very good. So you have those 2 sets of problems. A nice long weekend. Okay, that's all I have.
So is it a total of 4 for both 1 and 2?
Yes.
4?
Yeah.
So you just need to get 2 of the waters for the second one then,
I
right?
think so, because we ended up with, right. Yep.
Okay.
Yeah, but it's only 2 more, but it still is, you're doing the right thing, but you have to recognize that you got 2 from the baby, and you need 4 in the overall, so I only need 2 more. So you
Okay.
wouldn't go for 4, because then that'd be
Because
6.
then that would be open. Okay.
Yeah. So it's a little different, but yes.
Okay. So I thought I was.
Yeah.
So, okay, so what's the